Welcome to our channel. Let's begin the journey.
Today, we're stepping right into a high-stakes physics detective story. Imagine a world of glowing chalk, blackboard math, and a mystery that sits literally at the very center of every single atom in your body. We are going to tame the strong force, decipher this weird concept called mass defect, and unlock the absolute, staggering power of binding energy.
Okay, let's dive right in by confronting our central mystery. We all know the old rule. Like charges repel, right? So inside the tiny, super dense nucleus of an atom, you've got all these positively charged protons just crammed together. According to the electromagnetic force, specifically the Coulomb force, they should be violently pushing each other apart. I mean, they really want to get away from each other. So, why hasn't every atom in the universe just exploded by now?
To answer that, we have to look at the ultimate cosmic glue. Let's move to section 1, the nucleus paradox.
It turns out there's a serious cosmic tug-of-war going on. On one side, you have the Coulomb repulsive force, which is desperately trying to tear the nucleus apart. But entering the ring to counter it, we have a new player, the strong nuclear force. Now, for the nucleus to actually stay intact, this strong force has to be incredibly powerful. Like, it has to completely overpower that electromagnetic repulsion between the protons. You can think of it kind of like a ridiculously tight bungee cord. But here's the catch. It only works at astonishingly short distances, binding those protons and neutrons, which we collectively call nucleons, together in a microscopic space.
But how do we actually measure the strength of this cosmic glue? Well, that brings us to section 2, the missing mass mystery.
Prepare to have your mind bent just a little bit here. When physicists first started precisely weighing atoms, they stumbled onto a really bizarre phenomenon known as mass defect. It's the proven reality that an assembled nucleus actually weighs less than the sum of its individual separated parts. Take oxygen-16, for example. If you were to weigh its 8 protons and 8 neutrons totally separately and then weigh them all squished together as a bound oxygen nucleus, the bound nucleus is actually lighter by about 0.1369 atomic mass units, and this missing mass is a positive number for all stable nuclides.
Now, what's really interesting is the formula we use to figure this out. Delta M, that's our mass defect, equals the mass of the individual protons plus the mass of the individual neutrons minus the actual mass of the assembled nucleus. It perfectly calculates exactly how much mass just seemingly vanishes into thin air the moment a nucleus forms. But you know you can't just lose mass, so where exactly does it go?
To solve the mystery of the vanishing mass, we're moving on to section 3, Einstein's famous equation.
Here is the grand solution, folks, the ultimate aha moment. Albert Einstein brilliantly theorized that mass and energy aren't two separate things at all. Nope, they're two sides of the exact same coin. Mass is really just another form of energy. So when those nucleons bind together, that missing mass from our equation, it wasn't lost, it was instantly converted into binding energy. That's the exact energy required to hold the nucleus together against all that intense Coulomb repulsion.
And the crucial point here is the staggering conversion rate. Because the speed of light squared is such a ridiculously massive number. A tiny mount of mass yields a gargantuan amount of energy. In nuclear physics, just one single atomic mass unit converts to 931.5 mega-electron volts of energy. To put that into perspective, chemical reactions, like, say, burning coal, release energy in the range of single electron volts. Nuclear binding energy is operating on a scale that is literally millions of times greater.
So now that we know what binding energy is, we can actually map it out. Let's look at section 4, the binding energy curve.
I absolutely love this graph. It brilliantly illustrates what I like to call the cheat sheet of the cosmos. This curve plots the binding energy per nucleon against the mass number of the elements. Notice the shape we've got here. It rises steeply, hits a peak, and then sort of slowly tapers off. The absolute peak of nuclear stability lands right around iron 56. Nature absolutely loves stability, which means elements inherently want to move toward that exact peak.
Let's break down the geography of this curve a bit. On the far left, you've got light nuclei, with a mass number under 30. They have a relatively low binding energy per nucleon. Over on the far right, very heavy nuclei, anything over 170, they also have lower binding energy. Why? Because the nucleus is getting way too big, and that repulsive Coulomb force is really starting to fight back. So it's those medium-heavy nuclei, right in the middle, like iron, that are the most stable and tightly bound.
So, knowing that basically every element wants to be like iron, how does the universe, and how do human engineers exploit this exact curve to produce massive amounts of energy? That takes us to section 5, fission versus fusion.
It all basically comes down to two phenomenal processes. If you're a light element hanging out on the left side of the curve, you want to combine or fuse with other light elements so you can climb up toward iron. That's fusion. But if you're a heavy, unstable element on the far right, you want to split apart to become smaller, medium-weight elements. That's fission. Both of these processes result in products that have a higher binding energy per nucleon than what they started with. And that difference in energy, it gets released right out into the surrounding environment.
Let's look a bit closer at fission, since it's the process we actively use right now to power our cities. We typically use a specific isotope called uranium-235. But here's the thing, fission doesn't just happen efficiently all on its own, it's an induced process. We literally have to introduce a thermal neutron, which just means a slow-moving neutron, to the uranium nucleus to destabilize it.
Let's step inside a reactor and see how this builds like a chain of dominoes. Step 1, the slow neutron is absorbed by the U-235 nucleus. Step 2, it briefly becomes an excited, highly unstable intermediate nucleus. Step 3, it violently splits into two lighter, much more stable fragment nuclei. And step 4, this is where the magic happens, it spits out 2 to 3 brand new, fast neutrons. If we can slow those new neutrons down, they can go on to split more uranium, creating a continuous, self-sustaining chain reaction.
To safely harness this amazing power, human engineering created the nuclear reactor. The core contains 3 totally crucial components. First, the fuel rods, which are packed with that enriched U-235. Second, the moderators, usually water or graphite. These are absolutely essential because they physically slow down those fast neutrons so they can actually be absorbed by other uranium atoms. And third, the control rods. These act basically like the brakes. They absorb excess neutrons to ensure the chain reaction stays perfectly balanced and doesn't just run out of control.
Now for the massive so what factor. A single uranium-235 fission event releases roughly 200 mega-electron volts of energy. Compare that to burning just one carbon atom in a piece of coal, which releases about 4 electron volts. Let that sink in. Fission is millions of times more energy dense. It produces incredible amounts of heat, and it does it with practically zero greenhouse gas emissions during the reaction.
But what about fusion? Climbing the other side of that curve? Well, this is literal star power. Right now, in the core of our sun, hydrogen nuclei are fusing into helium. But to force positively charged protons together, remember, you have to completely overwhelm that Coulomb repulsion we talked about earlier. To pull that off, the sun relies on immense gravitational pressure and mind-boggling temperatures of about 15 million Kelvin.
And that brings us to the ultimate question for this explainer. We've mastered fission, but fusion produces minimal long-lived radioactive waste and uses isotopes that we can find abundantly in seawater. Right now, we're building experimental reactors to try and recreate the conditions of a star right here on Earth. Fission powers our cities today, for sure, but if we can fully master the star power of fusion, will it finally give humanity limitless clean energy? It is the next great chapter in our physics detective story, and honestly, it's one that could change the fate of our planet forever.
The view from here is breathtaking. Command, we are in position and ready for the next phase. If you liked the video, subscribe and comment the topic you want next. Thanks for watching, and stay unstoppable.